2.14 UTC, Goldstone's DSS-14 radar logged a clean Doppler curve, then a sudden residual. 3i Atlas picked up a lateral push, a few millimeters per second, in a direction no model predicted. Normally, a visitor skimming the inner system bows to gravity alone, with any extra nudge coming from sunlit jets that push anti-solar. But this kick angled sideways, as if a hand slid across the orbit, not along it. And here's where things take an unexpected turn. Across the globe, telescopes pivoted. What should have followed was a brightening spike, the signature of venting ices. Instead, photometry stayed stubbornly flat. Spectral measurements tell us which gases are escaping. CO and CO2 lines should flare when a comet flinches. They didn't. Solar physicists were divided. Some teams argued the radar was chasing noise. Others saw the same shift in fresh astrometry from Chile and the Canary Islands. From orbit, coronagraphs watched for any fan of dust. A coronagraph works by masking the sun, letting faint structures around a comet pop into view. Nothing obvious emerged. No plume to blame. That's unusual. Outgassing leaves, fingerprints in scattered light. And yet the sky stayed calm. Historically, we've been here before, but never like this. Oumuamua drifted with a mysterious, non-gravitational push. Borisov behaved like a textbook comet. 3i Atlas sits between and beyond, interstellar, active enough to perturb, quiet enough to confuse. Why would an interstellar object behave like this? Within hours, NASA, ESA, CNSA, and JAXA opened a shared channel, folding in amateur observers and radio arrays from 5 continents. Normally, international coordination refines a solution. Tonight, it sharpened the question. If jets aren't driving the change, what is? Theories multiplied. Some proposed ultra-porous, snowflake-like fragments, feeling exaggerated solar radiation pressure. Others pointed to delayed venting, volatile pockets opening after a thermal lag, like a kettle that whistles late. A few hinted at physics we don't yet name, while skeptics cautioned calibration and geometry. Tension rose with every frame. If a tiny force can rewrite a trajectory mid-pass, what unseen processes sculpt the paths between the stars? What hidden mechanism could produce such a transition? And then something even stranger emerged. As 3i Atlas rotated, the acceleration vector locked to a face that remained mostly in shadow, thrust from the dark side. The trajectory kinked again, subtle but real, and the acceleration vector stayed glued to a face that never saw dawn. Normally, cometary thrust comes from sunlit jets, ice warms, vapor vents, the push points roughly away from the sun. But here the impulse was phase-locked to the dark. Teams modeled thermal lag, where heat soaks into porous layers and drives delayed outgassing from shaded fractures. Others pointed to a hardened sunward crust that forced gases sideways. Either way, thrust from the night side was not the script we expected. The light curve broke routine. Normally, comets brighten in a smooth rise as sunlight and geometry favor the coma. 3i Atlas instead plateaued, then flickered with the rotation, as if vents blinked on and off behind a veil. Spectral measurements tell us what molecules are there by their fingerprints in light. A few instruments hinted at faint carbon dioxide lines. Others reported nothing but dust continuum. Solar physicists were divided. Was this chemistry? Or just our instruments straining at their limits? A coronagraph on ESA's solar orbiter caught the object's thin tail as it skirted the inner heliosphere. A coronagraph works by covering the sun's disk so faint structures nearby can be seen. The tail's angle didn't track the acceleration, another break from the norm. If jets were the culprit, we'd expect some alignment. JAXA's Subaru and ESO's VLT tightened astrometry, while NASA's radar at Goldstone pinged and mostly heard silence. No surprise for something that small and fast, but worth the try. And here's where things take an unexpected turn. The force scaled with rotation, not with sunlight. In classic cases, torque and thrust rise as the dayside warms. This time the beat was mechanical, like a vent locked beneath a lid. Some teams argued this pointed to volatile pockets trapped under a sintered crust, venting episodically into the cold. Others doubted the readings entirely, suspecting a geometry illusion or radiation pressure acting on ultralight dust sheets, an idea once floated for Oumuamua. This echoes the mystery of Oumuamua, which accelerated without an obvious coma. Back then, explanations ranged from exotic ices to fragile dust bunny aggregates. The difference now is the rotational lock. The push isn't simply sunward, it's tied to a face. If true, we're seeing engineering by geology, a natural nozzle shaped by alien weathering. Global networks moved as one. ESA and CNSA scheduled cross-hemisphere photometry to track phase changes continuously. Amateur astronomers stacked thousands of frames, smoothing noise to trace the flicker. A JWST target of opportunity captured a quick spectrum, its early, cautious verdict. If gas is present, it's faint. To understand why this matters, we need to look at how tiny forces compound over interstellar time. A whisper of thrust today becomes a canyon of difference tomorrow. If dark side venting can arise from unfamiliar crusts or fractal dust surfaces, how many worlds ejected into the void carry such subtle engines? Why would an interstellar object behave like this? What hidden mechanism could produce such a transition? Moments like this remind us how little we truly understand and how much the cosmos is willing to teach, one puzzling nudge at a time. But this was only the beginning, and here's where things take an unexpected turn. As 3I Atlas swept past Earth's orbit, its sky track kinked, subtle to the eye, unmistakable in the data. Normally, gravity alone draws a clean, predictable arc. This time there was a gentle but persistent shove, a non-gravitational nudge that said something on or within the object had switched on. Across the globe, astrometrists compared notes, and the residuals lined up in the same direction from Chile to Hawaii to the Canary Islands. Usually such offsets average away as atmospheric wiggles. Instead, NASA's JPL and ESA's dynamics teams refit the orbit and agreed. A real acceleration had entered the plot. The light curve added intrigue, flattening for a spell, then stepping brighter in uneven tiers. Normally, comets brighten in a smooth curve as sunlight intensifies. Here, the flicker looked like jets turning on and off with rotation. Patchy activity, not a uniform thaw. Spectral measurements told us what the eye could not. Faint signatures of carbon monoxide and carbon dioxide, but little water. Typically, close to the sun, water dominates the vapor. In 3I Atlas, super-volatile ices seemed to be doing the heavy lifting, hinting at a birthplace far colder than our comet nurseries. Coronagraph images sharpened the picture. A coronagraph works by blocking the glare of a bright source to reveal faint halos, and in the glare-tamed frames, the coma showed a lopsided fan that tilted over hours. Usually the dust points neatly away from the sun. Here, torque from uneven outgassing appeared to be twisting the spin and pushing the whole body sideways. Solar physicists were divided. Some teams argued this pointed to an ultra-porous, fractal surface where radiation pressure on dust grains adds to the thrust. Others doubted the readings entirely, suggesting calibration drift or a brief shedding of fragments masquerading as a sustained force. To understand why this matters, we need to look at the chorus of instruments that chimed in. JAXA and CNSA scheduled rapid response telescope time. ESA's Solar Orbiter Coronagraph searched the background for a whisper of the tale, and amateurs stitched nightly light curves from 3 continents. No single dataset was decisive. Together, they traced a story of a world being warmed into confession. History cast a long shadow. This echoed the mystery of Oumuamua's gentle push without a visible coma, yet differed from 2I Borisov's textbook cometary behavior. We haven't seen something like this since Rosetta watched jets on 67P subtly steer a nucleus, except now, the engine came from another star. Why would an interstellar object behave like this? What hidden mechanism could produce such a transition? Moments like this remind us how little we truly understand and how much an errant visitor can expand the map. Let's break this down. If outgassing can masquerade as a force field, then shape, porosity, and chemistry matter as much as mass and orbit. And if many interstellar travelers carry such quiet engines, our census of the galaxy's debris and the stories they tell about their home systems may need a rewrite, but this was only the beginning. Over one quiet night, the orbit fit for 3I Atlas jumped. Ephemeris updates from JPL and ESA's NEO Coordination Center nudged the flyby corridor sideways, a tiny shift on paper that meant a real force in space. Normally, gravity writes smooth arcs. Perturbations from sunlight and gas are footnotes. Here, the footnote became the plot. Teams interpreted it as a fresh burst of non-gravitational acceleration, an invisible hand likely powered by escaping volatiles. A stubborn light curve complicated the story. Normally, comets brighten in a predictable way as sunlight heats their surfaces. More heat, more gas, more glow. But 3I Atlas dimmed slightly and then brightened off schedule, as if its engine pulsed without warning. Spectral measurements tell us what's evaporating. Fingerprints of molecules etched into starlight. Keck and the VLT reported hints of carbon monoxide and carbon dioxide, while common cyanogen lines stayed weak, suggesting a colder, more exotic mix than most solar comets carry. A sudden change in the tail confirmed the push. SOHO and Solar Orbiter caught a kink, the dust plume pivoting like a weather vane. A coronagraph works by blocking the sun's glare, revealing faint structures around bright targets, and those structures move. Solar physicists were divided. Some pointed to solar wind fluctuations. Others argued the geometry better matched jets from the nucleus. Dynamicists mapped the timing to the trajectory shift and saw a match. An attempted radar ping from Goldstone returned only a whisper. Radar usually sketches shapes and spins. A strong echo means a compact, reflective surface. The smear here hinted at something fluffy and porous, a snowdrift more than a stone. That echoes Oumuamua's puzzle, low density, big effect. Yet unlike Oumuamua, 3I Atlas carries dust, a faint coma, evidence for gas doing the work. A global astrometric relay took over. CNSA's Purple Mountain Observatory, JAXA-linked telescopes in Hawaii, amateurs from Namibia to New Zealand, and Europe's multi-meter facilities fed fresh positions into the models. Some teams argued this pointed to localized vents on a tumbling body. Others doubted the readings entirely, proposing subtle biases from phase effects and asymmetric dust scattering. Why would an interstellar object behave like this? Then came a stranger twist. The acceleration vector rotated without a matching surge in brightness. The cause? Perhaps internal fractures rerouted gas, or the spin state precessed, swinging a jet away from our line of sight. In simple terms, the thruster stayed on while the nozzle moved. Moments like this remind us how little we truly understand, and how much an errant visitor can teach. But this was only the beginning. The shift began as a whisper. The predicted track slid a hair's breadth across the star field, and 3I Atlas was suddenly not where gravity alone said it should be. Normally, near-Earth passages are clockwork. Positions fall neatly on the ephemeris like beads on a string. This time the beads wandered. Teams at NASA's JPL and ESA's NEO Coordination Center refit the orbit and found the same culprit as before. A gentle push, but now angled differently. Scientists read this as a jet changing aim, not strength. The deeper implication is unsettling. Inside this object, forces are rearranging themselves in real time. Astrometrists from Chile to South Africa to Hawaii reported residuals that refused to average away. Typically, errors fade with more measurements and better star catalogs. Here, the offset persisted night after night. Some argued atmospheric dispersion or color terms were fooling the cameras. Others, including a global network of amateurs, confirmed the drift with independent setups. When many small eyes see the same nudge, the sky is telling the truth. High above the glare, coronagraphs on SOHO and NASA's Solar Orbiter caught the tail bending in a way sunlight alone couldn't explain. A coronagraph works by blocking the sun's disk, revealing faint structures near it. Normally, a comet's dust tail points away from the sun in a smooth arc driven by light pressure. Instead, 3I Atlas showed a kink, like a flag tugged by a hidden wind. Solar physicists were divided. Was this magnetic draping in the solar wind, or a jet sweeping the tail as the body precessed? The debate hints at a surface responsive to more than heat. Spectral measurements told a stranger story: weak water, stronger carbon monoxide, and a dust-poor coma. Usually near Earth's orbit, water vapor dominates cometary breath. Here, colder volatiles led. Some teams argued this pointed to a birthplace far from any star. Others noted it echoes the puzzle of Oumuamua, non-gravitational motion without the expected glow. Why would an interstellar object behave like this? Radio dishes and infrared telescopes joined in. ALMA chased faint gases. NEOWISE mapped warmth to gauge how heat soaks in and leaks out. Thermal inertia, how stubbornly a material holds heat, can torque a spinning body, changing where jets erupt. JAXA and CNSA analysts modeled fractures opening like valves, while NASA and ESA groups tested scenarios where a slight precession swings the nozzle with every rotation. What hidden mechanism could produce such a smooth, silent shove? And then, the philosophical weight settles in. If a small visitor can rewrite its own path mid-flight, how many tales of formation, chemistry, and stress are locked inside it? The Earth rolled beneath, the object sailed on, and our understanding, pulled by tiny, steady forces, shifted with it. At first light after the flyby, the orbit update didn't snap back. It drifted farther from the gravity-only path, a gentle, steady push still at work. Normally, once past Earth, a visitor settles into a predictable arc. This one kept sliding. Scientists read the signature of a non-gravitational force, small, continuous, and aligned with its spin, implying a directed vent, not a chaotic outburst. And here's where things take an unexpected turn. The shove looked engineered by geology, not intention. Through the night, the light curve smoothed into a repeating wave. Normally, comets brighten in a simple pattern tied to distance from the sun. Here, the peaks lagged the spin, hinting at a nozzle that swung like a lighthouse beam. Teams modeled a single active patch on a rotating surface, a natural thruster. The implication is profound. Structure and sunlight alone can guide a worldlet between the stars. Across twin hemispheres, spectra from Mauna Kea, La Palma, and Sutherland compared notes. Spectral measurements tell us what gases are escaping by parsing their colors into fingerprints. We expected water and carbon dioxide to dominate. Instead, observers saw an outsized role for carbon monoxide and faint lines from more complex organics. Some teams argued this pointed to ices buried beneath a thermally stiff crust. Others cautioned that faint lines can mislead. In orbit, coronagraphs aboard SOHO and Solar Orbiter traced a kinked dust tail. A coronagraph works by blocking the sun's glare to reveal faint structures nearby. Normally, tails align with solar radiation pressure. Here, a subtle bend tracked the rotating jet. That geometry strengthened the case for a single, persistent vent steering the object, not a random puff. Around the world, reactions fractured and converged in waves. NASA and ESA groups floated a delayed thaw model, heat sinking in, reaching a volatile pocket hours late. JAXA and CNSA analysts suggested layered ices from a colder nursery star, each layer waking at a different temperature. Solar physicists were divided. Was the solar wind helping to collimate the flow, or merely sculpting the dust after the fact? Some doubted the readings entirely, calling for more calibration. Amateur astronomers, stitching thousands of frames, kept the timeline honest. Then the history came rushing back. This echoes the mystery of Oumuamua, non-gravitational acceleration without a classic coma, yet differs in its steadiness and spectral clues. We haven't seen something like this since, and not with such coverage. 2I Borisov behaved like a textbook comet by comparison. Thriatlas sits between those stories, a bridge from the familiar to the strange. Meanwhile, deep space sentinels listened in. Parker Solar Probe skimmed the inner wind, feeding models of how charged particles might shear the jet. The Very Large Telescope's adaptive optics and radio arrays across continents hunted for dust sizes, seeking the grain physics behind the thrust. To understand why this matters, we need to look at origins. Composition encodes a star's climate in miniature. Why would an interstellar object behave like this? Perhaps its crust sintered under cosmic rays, trapping volatiles in pockets that vent through fractures, turning sunlight into guidance. If so, every wandering shard could be a slow, whispering archive of another system's seasons. Moments like this remind us how little we truly understand and how much the cosmos is willing to show. if we learn to read the gentle pushes. The first sign is subtle. The track of 3i Atlas on plotting screens bends a little more than gravity allows. Normally, a visitor skims past Earth along a smooth, predictable arc. This one twitches, like a sail catching a gust. Teams call it a non-gravitational push, the gentle thrust of venting ices, and the implication lands all at once. Sunlight is steering an alien shard. A sudden brightening follows a few hours later. Normally, comets brighten in a steady, distance-driven curve. Here, the light curve hiccups before settling, as if a buried pocket cracked open and exhaled. Spectral measurements tell us the gas isn't just water. There are colder volatiles mixed in, the kind that survive far from stars. That pattern fits an object forged under a different sun. And here's where things take an unexpected turn. A coronagraph works by masking the sun so faint, halos around small bodies can be seen. In those masked frames from ESA and NASA solar observatories, the coma fans asymmetrically, rotating like a slow sprinkler. If it's gas jets, the thrust should pulse with the spin. If it's sunlight pressure on dust, the push should track illumination more smoothly. The data show both rhythms. Around the world, scientists push and pull at the evidence. NASA navigators revise the ephemeris. ESA dynamics teams publish competing fits. JAXA modelers suggest a fractured crust acting as a thermal valve. CNSA researchers argue for ultra-porous materials feeling sunlight like a sail. Amateur observers, from Chilean deserts to Polish suburbs, time brief star dips as the object passes, sharpening its shape. The history echoes loudly. Oumuamua shifted without a visible coma. Borisov behaved like a classic comet. Atlas sits between them, a bridge and a contradiction. Some teams argue this points to a new class, ancient, space-hardened bodies that seal, store, and then stutter vent. Others doubt the readings entirely, wary of small systematics masquerading as physics. To understand why this matters, we need to look at how forces scale. Let's break this down. Sunlight pressure pushes continuously, strongest where the surface is fluffy and bright. Gas thrust depends on heat and fractures, turning on and off as the object rotates. When both are present, the path becomes a conversation between light and stone, one we can eavesdrop on. Deep space eyes join in. Parker Solar Probe and Solar Orbiter catch changing plumes from odd angles. ALMA listens for faint molecules. Subaru and Keck map the spin. A radio-quiet slice of Western Australia hosts coordinated radar attempts. Solar physicists are divided on the coma's fine structure, but the shared archive grows by the hour. Why would an interstellar object behave like this? What hidden mechanism could produce such a transition, from sealed stillness to whispering thrust? Moments like this remind us how little we truly understand, and how much patient skywatching can reveal. But this was only the beginning. As Earth falls behind and the sun fades, 3i Atlas faces colder light, and then something even stranger emerges. As Earth dwindles to a blue ember behind it, 3i Atlas should simply fade, but instead its light flickers in gentle, regular pulses. Normally, comets smooth out after perihelion. Here, the brightness breathes like a heartbeat. Teams interpret this as jets turning on and off with rotation, a lighthouse effect that hints at newly opened vents. The implication is a surface just now waking up to deeper heat stored months earlier. As tracking stations at NASA's Deep Space Network and ESA's EastRack refine the orbit, the path shows a subtle sideways bend, normally outgassing thrust points mostly away from the sun. Here, the push is lateral, as if the vents sit along an equator. Planetary dynamicists see spin-coupled jets. The deeper question is whether interstellar crusts fracture differently than those we know. As solar observatories pivot their gaze, coronagraphs catch a thread-like, sunward spike, an anti-tail. A coronagraph works by blocking the sun's glare, revealing faint structures nearby. Normally, dust streams trail away. Here, geometry and large grains stack along our line of sight, a telltale of fresh, mineral-heavy debris rushing ahead of the nucleus. As the object cools, spectra from Keck, VLT, and ALMA isolate cold gas lines. Spectral measurements tell us what's there by splitting light into fingerprints. Carbon monoxide glows. Cyanogen is weak. Water barely whispers. That's unusual. Activity this far out is usually water-starved and silent. Chemists read this as super-volatiles escaping from shaded pockets. As the data flow, scientists disagree. Some teams argue a delayed thermal wave finally reached a trapped reservoir, releasing CO sideways. Others doubt the lines entirely, blaming background contamination. Solar physicists were divided over the anti-tail, true grain sheet or coronal artifact. Even in consensus, the edges stay ragged. As amateurs from Chile to India post photometry, a pattern emerges. The rotation period lengthens. Normally, small torques barely nudge spin. Here, outgassing acts like a tiny brake. The change fits the pulses, turning light curves into a clock that maps the vents themselves. As models mature, a picture coalesces. A brittle crust cracked after perihelion, equatorial fissures vented CO, and large dust flakes behaved like sails, letting sunlight add a sideways whisper of thrust. It echoes the mystery of Oumuamua's gentle push, yet contrasts with Borisov's classic comet plume, signposts of a spectrum wider than we imagined. As agencies compare notes, NASA and ESA fast-track rapid response concepts. JAXA and CNSA discuss a shared microsat bus. The Comet Interceptor team studies whether its waiting spacecraft can pivot to a future 4i. The lesson is clear. The sky won't schedule surprises. Our hardware must. As the sun shrinks to a star, the pulses cease, the trajectory smooths, and the anti-tail dissolves, like a switch flipping off. Normally, activity ebbs gradually. Here, a reservoir was exhausted, a chamber emptied in the dark, leaving only silence and momentum. So why would an interstellar object behave like this? Perhaps because memory travels with matter, thermal histories, trapped gases, the scars of another sun. Moments like this remind us how little we truly understand and how much patient skywatching can reveal. And as 3i Atlas slips back into the deep, it leaves us a quiet challenge. Be ready for the next visitor and listen for its whisper.